Swayam Prabha. Digital India. Educated India.
Once again, I welcome you to this topic, soil mechanics topic, vertical stress distribution. And in the first session of this vertical stress distribution, I have shown the Bosniak's point load formula, various aspects of it, what are the assumptions, etc. And then the second lecture, what I have tried to show that though the Bosniak gave the formula for a point load, and our foundation generally is not a point. It is always we apply load through definite area. That means foundation will have different shape. Through that, actually, we apply the load. Then there is a mismatch with theory and our actual practice, and I have tried to show in the last lecture that how the point load formula can be approximately utilized for different shape of footing, particularly rectangular footing. We can divide into number of parts and then apply point load formula to each part, and then cumulative effect can be taken to get the effect of the entire loading area. And while doing that, we have shown also that when you are going to make smaller the mesh size, better will be the results. But at the same time, also highlighted that at a certain number of mesh size or certain number of mesh, that means divisions, you may not get that much improvement over the result. So, we can do 4 to 6, 8, 9, maximum 10 division we can make, and finally, we can get the results that will be good enough for most of the civil engineering application. So, that much I have shown. Next part is why I will divide into small part and apply point load formula separately. Instead of that, if I can integrate the effect, it is nothing but integration. I am taking a small part and I am putting another point, transferring to another point, then next point transferring to this point, next point transferring to this point. So, instead of doing this discrete one point, if I take a infinite number of points now, I can consider the foundation as an infinite number of point and infinite number of load, that is like a cube, and that actually if I imagine and your point load is applied, then I can just simply try to integrate that. So, through integration I can do better, because I have shown in the previous lecture that when you divide in a more number of parts, then we are getting better results. But now, if I integrate, that question will not arise. Directly I will integrate, because the effect of all will be taken through integration. So, that is the one we are trying to show, that integration, how we can do the integration for different areas. The area of foundation, one type of shape is circular foundation, there, but it is not in a very frequently comes, very special area only for circular foundation, but most popularly either rectangle or square or strip, this type of footings will be there, or sometime angle also will be there. So, different types of footing if it is there, how to integrate them to find out the pressure or stress at a particular point using Bosniak's theory. So, this is the intention of this lecture. So, we are trying to integrate the loading area using Bosniak's point load formula. So, to do that we are taking suppose hello, again it has gone, sorry, hello, please come. Okay. Okay. So, what I was trying to show here that instead of if there is a area and there is a load is applied through this area, and I was dividing into number of parts, and then I was taking to take the effect of these two here, effect of these two, or effect of these two here, effect of these two here, like that. So, instead of doing that, I will try to integrate. So, just a continuous, not a discrete one. So, to do this, if you see, the unit vertical stress on any given depth could be determined with acceptable accuracy by extending Bouguereau's equation to uniformly loaded circular area. So, suppose this is a circular area and it is loaded uniformly with, suppose, intensity of pressure is Q. And now, what I can do now right now, I'll because if this is the loading area applied with Q like this throughout the area, and so effect of everywhere. So, we can visualize that the stress intensity will be maximum below the center of the footing. So, what we are trying to do, and most of the time in the design we are interested to know the maximum value. So, because of that we are trying to show the now first integrate with respect to the center. So, if you want to integrate with respect to center, then what I am doing? I am taking a small element with d beta angle at a distance rho, and thickness is d rho, and this is the small area I have shown. This area will be rho times d beta will be the width, and thickness is d rho. So, that becomes dA. So, small area, this small area of the small parts, will be, I am considering this is a circular arc, then this circular arc will be what is r theta. Since at a distance rho and angle is d beta, so rho d beta is the arc length, and the arc length, outer arc and inner arc, the area, this will be little different. I can consider that the arc is taken up to the center of the element. In that case, I can consider that is the average width of the arc, average width multiplied by the average length, that is the arc length, and width is d rho. So, length divided average length multiplied by width will be your area. So, this is the small area we have got. Now, this small area and intensity is uniformly loaded footing. So, Q is there. So, you multiply by Q into d rho d beta. So, that become actually capital Q. This become capital Q. So, first I have got the small area multiplied by intensity, that become your Q. That means, now I want to find out this small area, which is, suppose instead of Q I can say this is dQ. So, because of this dQ point load, I want to find out the effect at the center. So, how to find out this one? The same point load formula will be applied, because this is the Q applied here at a distance rho. So, what is the effect? So, same formula I can apply, that means 3 Q. So, here instead of Q it will be dQ by 2 pi z square and 1 by 1 plus r, actually here rho square, and r is nothing but rho square by z square to the power 5 by 2. So, that means, for this small element I can use this equation, but when I want to do, suppose for entire area, then what I can do? I can integrate, and you can see dQ is a function of rho and beta, d rho and d beta. So, that is variable. So, I can integrate for beta from 0 to 360 degrees. I have taken a small angle d beta, and that d beta can vary from 0 to 360 degrees. I can integrate between 0 to 360, and I can integrate. Rho is varying when it is load. If I consider this point instead of here, if I consider here, it is lesser distance. If I take at the center itself, then r becomes 0. So, r can vary from 0 to radius of the footing. So, this thing if I do, then I can do simple integration, and by that integration I can get the stress intensity. That is the thing. Let me show you in the next slide in better way. So, you can see this same thing I have done. So, from Bosner's equation, actually it is a double integration is given. So, as I have told you that our expression is our expression is expression is 3 q by 2 pi z square 1 by 1 plus r square by z square to the power 5 by 2. So, now this q will be changing. Q will be your rho d rho d beta into q, that become q. If I have a substitute. So, you can see 3 small q 2 pi z cube, it has gone, and 0 to 2 pi 0 to r, and this is another form. This instead of this form, and we can write actually this equation I can write another form, that is 3 q z cube by 2 pi pi into 1 by 1 plus rho square plus z square to the power 5 by 2. This is also another form, 3 q z cube by 2 pi 3 q by 2 pi z cube into this is the form. So, I have used accordingly in this here. So, dq is substituted. So, q has gone, 3 into q has gone, this z q also came here, 2 pi is there already, and 0 to 2 pi, that is d beta to be integrated, and 0 to r rho to be integrated. So, rho by rho square plus z square d rho is there, and 5 by 2. So, now this is a double integration. So, for beta actually 0 to 2 pi, ultimately it will come 2 pi. So, it will be 3 q by z cube by 2 pi get cancelled. So, 0 to r rho d rho by rho square plus square 5 by 2. Now, by substitution method, rho square plus z square I can consider a constant something, and that can be again further substituted and integrated, and put the value finite integral limit 0 to r, and that is where r is the radius of the footing. If I put, then finally, I get a expression like this, that is your sigma z equal to q into, that is q actually is the intensity of the footing what is applied at the surface. This is surface footing intensity of q is given, and at any depth q minus this. So, that means 1 minus this, that means even go deeper and deeper, the stress obviously will be less, but through this equation we can get that. That means, so far by this integration what I have got, when there is a circular loaded applied load is applied through the circular footing, along the central line of the footing vertically below the footing, what is the stress intensity, that gives you this expression, but in not any other point. Any other point obviously intensity will be less, and we can also find out, but there is some method complication is there. So, that I am not discussing right now, later on we will discuss that. So, right now whatever we have got, it is at the at any vertical depth through the center of the footing, and which is critical. That means, when footing is loaded, circular footing, below the center of the footing stress will be supposed to be more, and we have got the expression for that. Okay. So, this is the one that is circular area to be integrated. Next one, when there is a rectangular area, that is the one, suppose the rectangle with size A and B, and then in that case how to do this integration. You can see here this is a x axis, from x axis at a distance, suppose dy, at a distance y, I have taken a small width dy, and from y axis at a distance x I have taken dx width. So, there is a, that means one small area I am getting of width dx and dy. That means, the area of this small part is dx into dy, and intensity of pressure on the footing is q. So, that means, this becomes dq. So, similarly we can apply that your point load formula, that was 3 q by 2 pi z cube divided by r square plus z square to the power 5 by 2. This is one form actually. If I simplify, it comes other form. So, this is the form. In this q to be substituted dq, see here, here actually since I am calculating. So, dq to be substituted by this. Okay. So, if you substitute this, you can see this q is there, 3 q by 2 pi will be there, z cube also will be there, and integral dy dx, and here actually instead of r square plus z square, if I go back to polar coordinate. So, r is nothing but this, r is nothing but under root x square plus y square. So, if I substitute r by x and y, so it will be under root x square plus y square plus z square, and that is the algebraic function we are getting, which has to be integrated. So, this integration is not very simple, but 2-3 time you have to substitute and integrate once for x and then integrate for y. So, twice you have to integrate. When you integrate for x, and then x will be varying 0 to a, and when you integrate for y, you will give the limit 0 to b, and after doing this double integration, we may get a equation something like this. I will show you the next slide. You can see this is the expression we are getting finally. This is looks a very long expression, and it has a mostly this expression contains two non-dimensional thing. One is a by z and b by z. Too many times if I write a by z, b by z in this equation looks very clumsy. Instead of that, it is introduced a by z equal to m, and b by z is taken as your n. And what is, suppose that means, if I have a footing like this, and then you have this is a, suppose, or this is a and this is suppose b, and then suppose I want to find out stress. So, here actually while integrating, what we have done, we have taken coordinate axis like this is x and this is y, and we have integrated with respect to this point. That means, this formula is applicable for the corner only. That means, throughout the area of the footing when loaded, and if I take the effect at this point, I am getting that. So, that is typically known as corner formula. This is called corner formula. That means, if I get a and b dimension, and it is entire area is loaded with intensity q. So, this is the expression. So, while calculating this, what you have to do? So, our calculation generally you have to find out at 2 meter depth below the corner of the footing, suppose this is the question. Then what happened? I know the a and b, and suppose z is given suppose 3 meter, and a is given suppose 2 meter, b is given suppose 2 meter. In that case, I have to find out m become a by z. So, 2 by 3, n also equal to b by z, b also 2. So, 2 by 3, or suppose if it is b is something else, then accordingly it will be changing. So, taking these two m and n value, you have to calculate this. Once you get calculate, then what you will get? I will get the entire area of the footing with dimension a and b when loaded with intensity small q, the at 2 meter or 3 meter depth, I will get the intensity if I use this value in this expression and get the stress. So, this is a very useful formula, though it is applicable for corner, but this formula in several combination can be used to apply different foundation shape or at different foundation location. So, that how this will be done, I will show in the next slide. You can see here whatever derivation we have done, this is suppose the typical foundation and with dimension is a and b. This is straight application of whatever formula we have given. So, we can consider this as a and this as b, and at this point suppose you want to find out the stress. So, directly we are applying the corner formula, but if instead of at this corner, if I want to find out the stress at some other point, suppose at the interior of this point of this foundation, then what I will do? I will pass draw a line parallel to the sides of the footing and passing through this point along lengthwise. I will also draw another line passing through this point parallel to the side of the footing and all through. Then you can see by this drawing two lines, I have got 4 parts 1, 2, 3, 4. Now, this for these 4 parts, what I have to do? I can consider now each separately. Suppose one I am considering footing 1, what is A, what is B? I will write A equal to how much, B equal to how much. That means, A is B is not constant. So, initially foundation dimension was A B. Now, I am using another small part. What is A for 1? What is A? What is B? What is your M? What is N? I have to find out, and then apply the corner formula. Then what I will get? I will get the effect of this foundation at this point. Okay. So, that means, by doing this I will find out, I will take foundation 1, I will see A, what is I will see B, then calculate M, calculate N, and then I calculate del sigma by using corner formula. Then that means, at a particular depth, because of this footing area I will get at this point. So, that will be so that is one thing. Similarly, I will take 2 footing 2, what is A, or suppose A 2 B 2, I will denote A 1 B 1 M 1 N 1 something like that, delta sigma 1 I will say. So, A 2 B 2, similarly M 2 N 2, similarly delta sigma 2 by using the formula. Similarly, I will take footing 3, suppose this one, what is A 3, what is B 3, what is M 3, what is N 3, similarly, what is delta sigma 3 from the equation by corner formula. Similarly, fourth one, what is A 4, what is B 4, what is M 4, what is N 4, and then after doing this, what is delta sigma 4 by using corner formula. That means, independently I have now got 4 rectangles and 4 times I have applied corner formula, and then I have got 4 values, delta sigma 1, delta sigma 2, delta sigma 3 and delta sigma 4. Then what will be my delta sigma? Delta sigma will be effect of all. So, delta sigma 1 plus delta sigma 2 plus delta sigma 3 plus delta sigma 4. So, this I will get. So, this is the way, that means, in various ways I can apply various combination, I can use the corner formula to find out the stress at different points. Now, suppose I want to find out at this point, I will just clean this one and then I will once again I will see, suppose this is another footing having the footing, and I want to find out pressure at this point. then what I will do? I will do a line I will draw parallel to the edges and passing through this point like this, then it divided into two parts 1 and 2. Then similarly, for 1 I will find out what is A 1, what is B 1, similarly what is M 1, what is N 1, what is delta sigma 1 from the equation. Okay. And similarly, for 2 I will find out what is A 2 equal to what is B 2 equal to what is M 2 equal to what is N 2 equal to, and then what is delta sigma 2 I will find out. Then what, after finding out this, then what will happen, because at this point effect of this rectangle and effect of both the rectangle will be there. So, because of that what I have to do, I have to find out delta sigma equal to delta sigma 1 plus delta sigma 2. So, this is the way one can do. Now, I will just consider another point where suppose I will show to the next one. You can see this is the case where I have to find out pressure at this point, which is outside the loading area. In that case, what I have to do, again similar to that, through this point I will draw a number of lines parallel to the sides. So, I have drawn one line here, another line here, and then from this I will extend to intersect this, from here also I will extend this to intersect this one, then I will get a bigger rectangle. So, instead of A B C D, now I am getting A I G E, and now again I will draw this line, I will extend up to this, and this line I will extend up to this. So, I will get now 1 part, 2 part, 3 part, 4 part. Now, what I can do, if I want to find out pressure at this point, what I have to do? I have to consider actually now I will consider, now this is a corner of this big rectangle. So, I can apply corner formula for this big rectangle, and then you can see that, but this portions it is not loaded. So, what I can do? I can imagine that this portion is negatively loaded. So, I will again apply corner formula for this, I will apply for corner formula this and with negative loading. So, it will be subtracted, and again I will apply corner formula again with negative loading, then again it will be subtracted, and by doing this what you can see, you can see that I am subtracting twice this area. So, that is again reducing. So, finally, I can again apply corner formula for this and add. So, that means I can find out delta sigma 1 for area A I G E with loading Q plus Q. I can find out delta sigma 2 with for D I G F this rectangle with minus Q. I can find out delta sigma 3 for H G E B with minus Q, and you can see I have calculated entire area with Q, and this area I have twice I have done. So, I can find out delta sigma 4 will be equal to this area H C H C F G with plus loading with plus Q. So, that means what is the meaning of this area? When I will consider this area, I have to find out what is A, what is B, and then apply corner formula, find out delta sigma 1. Similarly, when I will find out delta sigma 2, what I will do? I will find out this rectangle, what is A, what is B, what is M, what is N, then apply corner formula, then find out what is delta sigma 2 with negative loading. Then again I will consider this rectangle, I will find out for this rectangle what is A, what is B, what is M, what is N, apply corner formula, that I will again with negative loading I will calculate delta sigma 3, and I will consider at last this area what is A, what is B, what is M, what is N, and then delta sigma with positive loading, and then ultimately final loading will sigma will be delta sigma 1 minus delta sigma 2 minus delta sigma 3 plus delta sigma 4. So, like that I can get. So, now I will, if I do, that means I have subtracted this, I have subtracted this. Initially I have considered entire area, now I have subtracted this, now I have subtracted this, but I have subtracted twice, because of that I have added, and then I am getting delta 4. This is the way I can find out stress at this point because of this loading. So, like that any shape, suppose if there is a foundation shape is like this, and I want to find out pressure at this point or pressure at this point, accordingly I can divide it to like this or divide it to like this, and several points can be considered, and method of superposition can be applied to find out the stresses at different points. Like this is the application of corner formula. Again some more in approximate work I will do sometime, some other methods I will discuss in the subsequent lecture. Thank you.